0.6 billion parameter model, reasonable responses out at the start. But it does kind of go off the rails if you start scanning down here. Hey, welcome to the first new episode of Fine Tuning Fridays, a new series from the Oxen herd, where, as Cameron nicely put it, welcome to the Thunderdome. 2 models enter, and only one will be crowned the winner. So today is Qwen3, and specifically, I went for the smallest of the Qwen models because I, one, thought that would be the most fun to try to improve, and it's really fast to train this thing. It took like 10 minutes to end-to-end fine-tune it on 1,000 examples, and I ended up doing the full experiment on like 5,000 examples. Took 50 minutes, so really accessible, and you don't even need that big of a GPU to do it. And specifically, we're going to be looking at the task of text-to-SQL. This is a task that we use internally to our product on Oxen, and we're currently using GPT-4o in production. So I thought this would be like a nice real-world use case of querying data with, or generating SQL queries with an LLM. And we kind of have data that isn't in any of the benchmarks that we can test these models on. So the formula will be pretty consistent every time we do this. First, it's defining our task. Then it's collecting a data set, splitting it into training, test, and eval, your kind of classic ML flow. We'll evaluate an open source model on the eval set, evaluate a closed source model, then we'll fine tune the open source model, do another evaluation, and then at the end of it, we will come up with a little table that looks like this. And here is a little sneak preview of the numbers to motivate the rest of the session. So right out of the gate, GPT-4o got 45% accuracy on this text-to-SQL task that we had. The base Qwen 0.6 model did really poorly, 8% out of the gate. It didn't really understand the assignment. But after fine-tuning that 0.6 model, got it all the way up to 42% accuracy. And last night, just for one final experiment, I kicked off the 1.7 billion parameter model on the same data set, and that one actually surpassed GPT-4o. So I'll walk through all of the fine-tuning code there and kind of chat through how this is actually really accessible if you do have a data set. I kicked off this last fine-tune while we were at the airport at like 11 p.m. and Scott and I's flight was delayed for an hour. So that was a really fun use of time while we were there. And so more concretely, to walk through the workflow that we're going to be doing, I kind of put together this diagram of the flow that we'll be going through. So defining a task, collating the data sets. We actually grabbed some of this data from our public repositories and public queries that had been run on them, split into the train and test data. We'll have 3 models that kind of go through the same pipeline of running the prompt and the model on the data set, getting a result set, running an LLM as a judge, and we'll see why we need to do that in this case. Having a data set that's all the judgment results, and then extracting the accuracy. So these are kind of like reusable pipelines that I put together over and over again to make this a little easier and more formulaic as we go along. So the task, specifically, we have this feature within Oxen AI, and if you're new, Oxen AI is a tool to store large machine learning data sets. You can explore them, you can version them, you can branch them, you can kick off jobs to fine-tune models, etc. And it's all versioned and all kind of like a GitHub-like experience for these data sets. But one of the features that we have within there is if you have a data set, you can just type a query in natural language, and we will convert that to a SQL statement for you that will run on the data. So an example of this is, let me try to pull up this link here. We have this repository of images of Ox with wings. These things get generated anytime somebody stars our GitHub repository. You can see we were using some older stable diffusion models for this, so some of them don't have wings, some of them do. It's kind of just a fun little thing that we've wired up. But the cool part here is you can say, like, find all the rows where the prompt mentions a yellow ox, or maybe I'll change this to a green ox, and we will translate that to the SQL statement, run it on the data set, and then that kind of helps you explore the data as you're putting together your training or fine-tuning data sets. And so under the hood, we have a model that takes in this prompt. We have a little system prompt. It takes in the schema of the data frame itself, and then it's going to be outputting the SQL statement. So this isn't a super complicated SQL statement, but sometimes, I forget if it's like and where to put these percentage marks, and it's just a nice little abstraction layer to make the querying a bit easier. And so the model that we're currently using under the hood is GPT-4o. And our question is, can we take Qwen3 and get it to a similar performance? As we saw from the numbers, we can indeed do that. And so we'll be walking through concretely what prompts we're using, what the data set looks like, and how we got there. This is the prompt that's running behind the scenes. So write a SQL statement that's equivalent to the natural language user query below. You're given the schema in the format of a create table statement. Assume that the table is called df. We'll get into that a little more later. Do not give any preamble or extra characters or markdown, just the SQL in plain text, and make sure the SQL query is on one line. We then populate the schema here and the user query here, and then try to have the LLM output the SQL query here. And to make this a little more concrete, let's look at the data that we're going to evaluate this thing on. So before you it's really tempting to dive right into the fine tuning. That's the fun part. That's the part where you're training the model. But it's good to take a step back and really understand what problem you're solving. And honestly, the best data or data set that you can evaluate is the data that flows in and out of your production system. So we actually took some data from our production system and some data from just like public text-to-SQL benchmarks and put it together into a data set that looked like this. So you can see there's a bunch of queries, there's a bunch of schemas of the underlying tables. Decided to put those in the format of create table statements, just so it's like also SQL that the model's seeing when it's trying to generate SQL. And then here's the ground truth SQL statement that should be generated given these two things. A couple things to note here, we're just working in the single table setting. There is text-to-SQL problems where you might want to do join statements across tables, or you might have like a more complicated full query that needs to run multiple steps, or like an agentic workflow. We really, for our use case, we just have a single, Parquet file that we're querying. And so under the hood, we call these tables df, and this is a really constrained version of the problem. But you can see we have a bunch of different open source data sets that I collated here, and including some of the data from our public repositories that people have queried in the past. So you can even be like, what is the distribution of sources sorted by count, just to give us a sense of the distribution from these different data sets. WikiSQL is the highest one. We have SQL create context, and then about 700 from the Oxen production system. These ones actually tend to be some of the easier queries in the data set because they are things like find me all the rows that do this or give me a distribution. So I found throughout the experiments that adding more Oxen data made the accuracy go up because it was actually a slightly easier task than some of these other ones. But that gives you kind of a sense of the shape of the data that we'll be working with. We had about 8,500 examples in there, if you look at the row count here. So the first thing that I did was just split that into train, test, and validation sets. So the training data set ended up having 5,000 rows. And then for quick iteration, I was using this validation data set that had 200 rows just to kind of get the core loop going. It's probably better in practice to have thousands of eval or validation set examples, or have a bigger test set, but this was just a good starting point to get the whole loop going end to end. So now that we have our data sets split, the first thing that I wanted to do was evaluate a strong model. So I tend to find that when you're going into the fine-tuning process, like we have all these big foundation models that are out there today, and if they can't solve the task, it's probably likely that you either didn't formulate your problem very well, or you don't have the right data, or there's just something off with your prompt. It's nice to check yourself on a really state-of-the-art model before you go into the fine-tuning, because there might just be some obvious things that you're missing, like, oh, well, I didn't give it access to the schema, so how is it going to generate the SQL statement? Or one thing that we thought of while we were going through this, yes, we're giving the query and the schema, but what if we gave the first 5 rows as well? Because like it wouldn't just from the query and the schema have access to what are the values in the source column. So there's a bunch of things that you can think through of like adding to the context or adding to the prompt for fine tuning, just by running your first experiment on the strong model. So we have some tools within Oxen to help this process. Namely, we have the ability to pick a model and run it on a data set with a prompt. So this is the prompt that we had before. You can see we ran it on all 2,000 rows. We kind of give you a sense of how many tokens was used. Took 10 cents to run this thing on here. And so what we ended up with is we started with a data set of query, schema, SQL, and source, and ended up with this new column called prediction that came from GPT-4o. So you can see in this case, the SQL and the prediction did line up. So got that one right. It looks like there's a little white space discrepancy between these two. So that wouldn't be a direct string match, but that does look pretty correct. And then you run into things like this, where you might have one version of the SQL that's like select count star, and one that's select count distinct and a name. And depending on what the query is that came in, both of those could be those could be valid SQL statements for the query. I think we actually have a more concrete one where this one. Yeah, this is a great example where you might have like a and primitive at the end here, and the model got it right. It just like swapped which predicates were where. So it had the gain is greater than 319 in the start, and name equals Derek Lock at the end. There's even things like, are we using quotes or not? So it's actually not just like a direct string match that we can do here to understand how well this model did on this data set. I did start with direct string matches just to get a sense of what that accuracy would be. So we can say like, what is the, or find me all the rows where query, or no, where SQL is equal to the prediction. This will just give you like a raw count of how many times SQL directly matches the prediction. And you can see this filtered it down to 22 rows. So out of the 200, there's actually only 22 that had a direct string match between the SQL that we expected and the prediction that came out of the model. So this immediately triggers in my brain, okay, maybe we need to do some sort of LLM as a judge to compare these things. Because if you give, let's look at some of the places that they do not line up. If you give an LLM these two things, granted, this one could be done with just like a trim operation on the string, but maybe let's look at this one. If you give an LLM these two SQL statements, hopefully it'll be able, and the query and the schema, hopefully it'll be able to tell us whether they're equivalent or not. So that's the next thing I did, was try to come up with an LLM as a judge query that we could run on all of this data to see what our accuracy is more like, because I doubt that it's 11%, given some of those examples that we saw that were like close, but not quite there. So I ended up using the Google Gemini model to be LLM as a judge. Let's wrap this code so we can kind of see what the prompt looks like. And make it plain text so we're not looking at weird highlights. So compare the following SQL statements given the database table to see if they're equivalent. If they're not the same, give a reason as to why. Format your response between two XML tags, one for the reasoning and one for a true-false statement indicating whether or not the statements are the same. Again, don't include any markdown surrounding XML, and give it a little example of the output that I want. So I thought this would be a nice way to, one, have the LLM give a little thought process before it decides on whether these two answers are right or wrong, and then put the true false in a nicely formulated XML tag that we could extract those out of. And then I give the schema, I give SQL statement 1, and I give the prediction out of the model. And so what that looks like concretely after we run the model on the data set, and like I said, I used Google Gemini Flash for this just to have, I didn't want GPT-4o judging the results that GPT-4o spit out, because sometimes models like to prefer themselves. So I chose a different model for the LLM as a judge. And you can see the judgments come out like this. And it has a reason in XML tags up here, and then its final answer of whether these two are equivalent or not in here. And you can see it calls out that there is not a hyphen within this string. So technically it will select different sets of rows here, and these two are not equivalent. This one, it says the SQL statements are exactly the same. That's great. And so we just have these true false statements that now we can extract out of the rows. In order to extract these out of the rows, I actually wrote a quick notebook to do that. I just called it extract accuracy.py. Oxen kind of has all these little tools in your tool belt that you can string together to do these processes, kind of in the big diagram that I showed above. So I wrote a little Python notebook. If you're not familiar, I'm really digging this Marimo product. It's like Jupyter Notebooks, but if they did it well, in my opinion. So we can take this results file here, I can just put it into the little tool that I built here. You can run these things in app mode or in edit mode, so you can see like just the UI of the tool that you want to build, or you can see all of the raw code here. And it looks like I actually grabbed the wrong data set. Let's look at results. Valid GPT-4o judgments. This is the one with all of the judgments in the column here that I wanted to run. You can see it was missing the judgment column. That's how I figured that out. And boom, we got 90 out of the 200 correct. So that's where I got that 45% accuracy for GPT-4o at the start. So I'll pause there because that's kind of like the first end-to-end workflow on a model to get an accuracy. Are there any questions, any thoughts, anything top of mind from you guys before we dive into the fine-tuning part?
I'm excited to try out Marimo notebooks, Greg.
Yeah, they're really cool. Let me show you some things that I really like about them. So one is that all of the cells get put into a directed acyclic graph. So if you update a cell at the top, it computes all the variables that were used in cells down below and reruns it in the same order every time. So with Jupyter notebooks, you can run cells kind of willy-nilly all over the place, which
Yep.
can be nice, but then it's not reproducible when you share it with somebody else. And then the other thing is that these get stored in raw Python. So they're just like decorators that instantiate the cells. You can see this is how they create the graph is they know all the things that are returned from one cell into another. With Jupyter notebooks, all this gets stored in like this crazy JSON schema. So if you make a little update, commit it and push it, and I make an update, it's really hard to see within the JSON what we change. With Marimo, it's just raw Python. So you can see the changes really easily between version 1 and version 2.
Yeah, the
So
huge part is that it's stateless, so it's not taking all that cropped with it.
Yeah, yeah, exactly.
Greg, does it make it easier to present what is happening big picture in a notebook, like when you're presenting to a group of people?
I think it definitely makes it more reproducible. They do have nice UI elements, kind of like I showed, and they have charts and graphs.
Yeah. Oh.
We go to their.
Oh, that's right. That was the first thing you said.
They use a lot of Altair stuff, right?
Yeah, yeah. So here's like an example where they're exploring embeddings using it. I wish I could fast forward this video a bit, but you'll see that they have really nice. He's editing it real time. It's updating the UI as the edits are being made. And then you can create things like sliders that also, as you're updating the slider, it's like updating the UI below. And then here's an example of the Altair chart that they'll pull up. There we go. So now, yeah.
It's like turning a notebook into a React app, basically.
Yeah, exactly.
Oh, wow. Cool. Thank you.
Yeah. Cool. So that's what we use to take the raw, just
Greg,
reasoning. Yeah.
There are a couple of questions in the chat. It's just hard for me to read them right now.
Okay. Let me see if I can pull up chat. I have my screen.
I can read them if you'd like, Greg.
Yeah. Can you do that, Matthias? Thanks.
Yeah. Let me find them really quick.
I will say regarding Marimo, I have grudgingly really come to enjoy the MB dev approach. And so, I mean, it looks like they're on their way, but just the having NB dev It's based on Jupyter and Qwen3.0, but just having it able to spit out code and docs while still having notebooks to play around with is really nice. I would love it if they would integrate Marimo instead of Jupyter, but they're not there.
Interesting. Would that be something you think the Marimo team could dive in and help with, or does the NB dev team need to buy?
I think I and a couple of other people have suggested it to them, and they are integrating. I mean, you can do a lot more with Marimo. It's just having that one-to-many workflow is so nice.
Got it.
I mean, there are plenty of headaches because Qwen3.0 is not simple, and neither is Jupyter. So there are all kinds of sharp edges in NBDev, but once you get it working and you have everything just, as soon as you run it, it's spitting out all these separate artifacts that you can use in a code base is really nice. And it can publish to PyPy and stuff like that.
That is cool. Nice.
So I have a couple questions here. One of them would be, have you tried using JSON output and might have been better at making the output more consistent? Alternatively, you can use the OpenAI beta client where you can use Pydantic base model to define the output format for the model.
Yeah, I did think about that. It was just easiest for me to output some XML and parse it out, but I think you could totally be flexible with the inputs and outputs there. I don't know. It would be interesting to see how much effect it would have on performance, or if it's just a developer experience improvement. I actually don't know.
Another question would be, why not parse a string using SQL parser, Apache Calcite, for example?
Oh, that would be another great way to check if it's correct or not. I think even the best way would be to execute the SQL statement on a table and have the ground truth be the result set. I think that would be the best way to do it. We just didn't have access to those tools, and this was the fastest way to get an eval up and running. And I think that's just a good practice in general, is like get yourself to some benchmark score and get yourself to some data that you can actually look at. And then you can start making these tweaks of like, oh, I see a really common pattern of mistakes. That was either a problem with my evaluation or a problem with how I formulated the problem. And then you can tweak that and you can start iteratively making it better. So it's a great suggestion too.
All right, one more. If Gemini is strong enough to judge, why don't we use it to distill other models?
Yeah, I think that's totally in the realm of possibilities. There's so many models out there today that you could generate either synthetic data or have. I think this is a great candidate for some sort of reinforcement loop as well, even using the SQL compiler as feedback or running it on your actual database tables if you have a sandbox. So yeah, I think tweaking the models is definitely in the realm of next experiments that could be run. Cool. All right, let's get to the small guy, Qwen3.0-6 billion. So a couple things to note about Qwen3. It was trained on an insane amount of data. I think it was like 36 trillion tokens that these Qwen models were trained on. It might be actually fun to even look at the paper for a quick overview of some of these things. Let me find the link. But Qwen, and this will open in a second, but Qwen has kind of two modes of operation. One is the thinking mode and one is the non-thinking mode. So that's one of the benefits of the way that they trained this model. And they had a really nice diagram of the full process down in here. They kind of did a similar post-training flow to the DeepSeek models, which we covered at the start of the year. And they released a bunch of different models, and I think this diagram's helpful for you to help make a decision of which ones you use. But they kind of have the flagship models here of the 235 billion parameter model, MOE with 22 billion active weights. And then they have Qwen3.0-6B. And they call these two their flagship models. So they have the highest performance on a lot of the benchmarks. And they went through the full like pre-training and then post-training to do chain of thought reasoning, a reasoning RL stage on top of that, similar to the DeepSeek models. They then train it to have the thinking and non-thinking modes. So we'll see how we toggle those on and off. Then they do a general RL stage, and then they get these big flagship models out. All of the lightweight models started from a same pre-training step, but they actually just used synthetic data from the flagship models to distill all of these smaller models. And so the smaller models are 14 billion, 8 billion, 4 billion, 1.7, and 0.6 billion. These are the two that I touched on at the start. But that's kind of the breakdown of, they actually did do a distillation process from the large models to get this suite of smaller ones that we'll be working with. And under the hood, they have special tokens that you can put into the prompt to enable thinking mode or reasoning mode and non-thinking mode. So the first thing that they have is just this think XML tag. That's another reason that I was kind of formulating some of the downstream things as XML tags, was just to be a little more consistent with this. And then they have these tokens that they injected in and out of the training data in random places so that it would trigger the model to think or not think. In the test that I was doing, I actually ran everything in non-thinking mode just because we want that text-to-SQL to be really quick for the user, and we don't necessarily need all of those reasoning tokens going on before we come to the answer. Maybe if we set up faster inference, we could have the thinking time and get a higher accuracy, but I kind of went with non-thinking mode here. And we'll look at some of the raw system prompts for real examples of this, but you can kind of see this is the underlying format. And if you do put these like an open, you start your assistant with an open think tag, it'll start thinking, it'll close it, and then it'll put the response, which is pretty cool that you have one model that can do both modes, because it was kind of trained to in the post-training step. So that's a little background on Qwen. So the first thing that I did, because these Qwen models actually aren't available in many of the APIs that are available, I actually just put together a Marimo notebook that would run the model on a data set. So I was spinning these up on like an A10 GPU with 8 cores and 8 gigabytes of RAM. You could technically run these things on a CPU if you wanted, because they're so small, or even on your MacBook with like the M series chip. I just wanted to run it on a GPU to have the inference be a little faster. But the main things that I kind of want to point out are, and I have different modes that you can load the model in after we fine-tuned it. So loading the fine-tuned model, loading the parameter efficient version of the fine-tuned model, and loading the base model. But this predict function is kind of the main thing that you need to think about if you're running these things yourself. And to either enable or disable the thinking, they have this nice parameter just directly in their apply chat template function that can take in a list of messages, and then it'll output a string that looks like this. So within the Hugging Face library, they implemented enable thinking true or enable thinking false. And under the hood, they take care of constructing that string before you put it into the actual tokenizer and run it through the model. So if you're using these things just locally or through raw Python, this is an important flag to use or not use. And then I have that same prompt that I was using with the GPT-4o, but as the system prompt in my predictions. And so once this script gets kicked off and finished, it saved all of the results back to Oxen and in a data set that looked like this. And for debugging purposes, I actually put the raw prompt in here as well, so we could kind of take a look. And sometimes it's nice to even see that you formatted this raw text well. But if you put it in the non-thinking mode, that apply chat template will actually put an open think and a close think right at the end after your assistant. And that'll just tell it, hey, we're not in thinking mode right now. And it will generate the response. So you can see here, evaluating the 0.6 billion parameter model, we get some reasonable responses out at the start. Like this is another example of the ands kind of swapped, but generally got that one correct. But it does kind of go off the rails if you start scanning down here. It actually creates table statements in its prediction. It just spits back out the query sometimes. It's a bit unhinged, this very small 0.6 before you fine tune it. And so end to end, I went through the same pipeline, and this one actually just got 8% of the evaluation set correct. And even just scanning, these rows here, you can kind of see why it doesn't really understand what we're doing yet. It is a very small model that's not super general, so I wouldn't expect it to do that great out of the gate. So I ran the same LLM as a judge process, ran the same end to end, and this got 8% accuracy. It's the TLDR. So now that we have 8% as the baseline for the 0.6 parameter model and 45% for the GPT, it's time to get to the fine tuning, the fun part. We've got our baselines set up, and now I actually wrote this fine tune in a notebook as well. Similar requirements here. I just used an A10. You could probably get away with a T4 or an L4 looking at the actual memory usage as we went along. But oops, need to do that. Let's kick this off and give you a sense of what the fine tuning actually looks like. Cool. So I have this train function here that can take in whatever base model we want to start with, whatever repository we want to pull the data from. It instantiates the model, which is kind of your just standard auto model for causal LM and auto tokenizer. And you got to make sure if you're running it on the GPU to have device map equals auto here. We then are just using all of the Hugging Face libraries here. I know there's different fine-tuning tools out there like Unsloth or Axolotl that I've heard good things of, but I honestly like just using the SFT trainer from Hugging Face as a good starting point or baseline. If you start running out of memory or you start running into performance issues, for sure, try some of those other libraries, but a lot of the defaults from the SFT config and the SFT trainer are a great place to start. We pull in the data set that we had from Oxen with the schema, the user query, and we kind of collate that into these messages. We do the same thing during inference to apply the chat template with the enable thinking equals false. And then we just put that into the text that's going to be fed into the model. And at this point, we also have the ground truth response in there. So it would be like a text block similar to what we saw before, but with the SQL as the correct answer there at the bottom. And so I'll kick this off to give you guys a sense. Actually, it might be fun to do this with like a larger model that I haven't tried yet. I think this is the name of it. Yeah, that looks right. Let's kick this off with the 4 billion parameter model, and maybe I can have another number for tomorrow when we actually publish this. First thing it does is actually download those model weights from Hugging Face. So that's going to take a little second there. So we'll go through a little more of the code while that's going. I do have options for you to load it in parameter efficient mode. I actually did do a full fine tuning in the other examples because it is such a small model and it didn't take very much GPU VRAM to do it. You'll see when the model's actually loaded, Marimo has some nice CPU usage, memory usage, and you can see how much GPU, there we go. It's starting to load the model into RAM or into VRAM right now. So you can kind of monitor as you're going along whether or not you have the RAM to do a full fine tuning or not. You can see now it's downloaded the data set, it's tokenizing all of the examples, and it's started to kick off the train, and CUDA's out of memory. So this is like usually how these things start is, okay, you pick a model, you download the weights, you see if it can fit on the GPU that you're currently running. If not, I have this nice little flag to run it in parameter efficient mode. And we could kick that off with parameter efficient fine tuning and see if that actually fits in. Or you could just kill this thing, grab a larger GPU, and train the 4 billion parameter model on that. But if you've ever done fine tuning, I feel like the out of memory errors are the first thing that you really run into and have to figure out what compute requirements you have for that particular model. The initial experiment that I did used that NVIDIA A10 with 8 cores and 8 gigabytes of RAM. I actually did the first experiment with just 1,000 examples in the training set, and that only took 10 to 12 minutes to fine tune the small one end to end. And it's really nice to have these small experiments before you kick off like a really large one, just to know that the end-to-end model weights get saved correctly, that you can load them back into your eval. There's like a lot of other steps that you have to consider. And so it's nice just to do this really short experiment to make sure you can wire all the things together, then crank up the number of examples, then maybe try a larger model, etc. But that's kind of how I like to go through this process. After it's done, these scripts save the model weights back to a branch that was created. So you can see this was the one that I did 13 hours ago from the airport. And it just dumped all of the model weights into this directory here with the logs for all of the like learning rate and loss and all of that stuff. And then these are the raw safe tensors that you can load back into your eval script. I like to just have these experiments on a bunch of different branches so that I can toss them out if one didn't work and keep the kind of main Oxen branch really lightweight here. one cool thing about Oxen, unlike Git, is that if you keep your main branch really lightweight, if you clone that data set, it doesn't clone every single object that you have on every single branch like Git would. So you can end up having tens of gigabytes within your repository, but just have the data branch be really lightweight and have all of these model branches be a little heavier. So once that model finished training, I did the same kind of eval notebook to run it on the same data set. It got all of these predictions out, and just scanning down here, you can see, okay, we no longer have all of these create table statements at the start. If you go one by one, wow, like the model is actually doing the correct syntax here. This one was an interesting one that it got wrong. I remember looking at it, didn't know whether to put an underscore in block floor or have it be together. And if you look at the query, it's like what nurses are on call on block floor 1 and block code 1. Tell me their names. It does have the correct not underscore here. So it's curious that the model didn't pick that up and just decided to go straight from the query to try to put an underscore in it. But these are the kind of things you'll only really see by looking at the data after you go through, and maybe we need to choose a larger model. Maybe we need to have more examples in our training data set that have stuff that look like this. But those are the things you can start iterating on and tweaking once you look at the things that it gets wrong. So if we just did like a raw string match here, so find all the rows. Fiction. I think if I remember correctly, yeah, this already has like a higher accuracy just for a direct string match than GPT-4o. But when we did the actual LLM as a judge, it ended up being 42 or 43% accuracy. Running those same exact steps, and let's just pull back up the chart at the end here. Yeah, 42. So it actually did better at just like the direct string match thing. If you remember, GPT-4o was like 22% direct string match, 45% LLM as a judge. This one was like 37% direct string match, 42 LLM as a judge. And then I ran the same script, just bumping up the size of the model, and that bumped us over 57% on this validation set. So that's kind of the end-to-end workflow here. I think there's still more experimentation. There's still more debugging I'd like to do on within this error set, like what are the types of errors it's making? Is it the not following the schema? Is it maybe if we added more rows to the context, it would do better? But it does really make you think that, hey, it is possible just to take these small models, especially if you have a really well-defined task, and have much more control over the end-to-end rather than just tweaking the prompt and trying to iterate on that. So really encouraging first experiments here. It's kind of cool seeing Oxen come together and be able to run all of these experiments all in the platform. So if you guys want to give that a try, we have those notebooks, we have the ability to run models on data sets, etc. And we're actually partnering with Baseten. I don't know if you guys know them for further work on inference. They have like a really nice inference API for a lot of these large models, but we're partnering with them on some training infrastructure so that you won't just be able to select like an A10 or an H100, but you'll be able to spin up a whole cluster to do larger scale fine tunings. And we're going to wire that up directly to a data set so that you can kind of one click go from data set to model and then just kind of sit back and enjoy. So stay tuned as we're rolling that out. If you are in the San Francisco or Bay Area next week, or no, June 4th, we'll be doing an event up there with the folks at Baseten at the AI Engineering World's Fair called Damn You Fine Tuned. And that'll kind of be like a happy hour and launch for some of this training infrastructure. So if you want like hang out with us live in person in SF, we'll be there. Or if you want access, if you have larger fine-tuned jobs that you need infrastructure for, we're happy to sponsor that for beta testers just to like get this end-to-end flow going. So come to us if you want free compute and you have big data sets. So that's all I had for today. I'll stop the share, stop the record, and maybe we can jam and have any questions live after the chat. But if you're watching on YouTube or anything like that, we'll see you next time.